presentation. The title of my presentation, as per invitation, is Energy Management Strategies for Fuel Cell Battery Hybrid Underwater Vehicles. But just like most of us did, I will start with a brief introduction to my PhD topic, and then I will continue with my energy management presentation. So that didn't work. So the title of my PhD is System Performance Optimization for Underwater Vehicles. Performance is a very, very wide topic, and the word is more of a buzzword than actually something very concrete. So we could see performance as a combination of aspects of reliability, autonomy, maneuverability and control, speed, and endurance. And in SMaRC, we work on most of these topics. And my focus is on endurance. And if we have a closer look on endurance in itself, then we see it's influenced by control strategies, hydromechanics, reliability, which are topics that I don't focus on very much, but I focus on propulsion systems and energy systems. In the last SMaRC Academy, I have already presented the propulsion systems. I did a study of underwater gliding compared to propeller-driven propulsion. And now I'm focusing on energy systems. And just a brief slide on the motivation, why to increase endurance. And there are basically two reasons why to do so, because we can get into areas that we couldn't get into before. And most interesting are under the ice shelves, those areas, which are up to 500 kilometers one way. And that's a really long journey for an underwater vehicle. And the second reason is reduced costs, because if you can stay out with your AUV for a longer time, you need the ship a lot less. And yeah, so as I said, the second branch of my PhD is on energy systems. And here I focus mostly on fuel cell systems for underwater vehicles. And brief history of AUV fuel cell systems. The development of fuel cell systems for AUVs already started just before the year 2000, in like 1998, 1999. That's when the Japanese research team from JAMSTEC and also the German team from Atlas Electronics started developing rather big AUVs with fuel cells. And they operated them maybe until the mid 2000s. And that's when they slowly started to switch to other energy sources for various reasons. And then in around 2009, 2010, the French research group from Ifremer, they had their own fuel cell powered AUV. And now in the last 5 years, we've had the Norwegian FFE, which is basically the equivalent to the Swedish FOI. And also JAMSTEC, again, the same Japanese research group. They came up with new designs and new prototypes. And also last year, the most famous maybe and the most recent is the Canadian cellular robotics Solos long range AUV, which looks very, very promising. And I'm looking forward to see some data from that AUV, because it has a really modern fuel cell system. And there have been a few conceptual designs as well throughout the years. And we are also working on a conceptual design and hoping to actually turn it into reality soon. So introducing to fuel cell systems for underwater vehicles, what exactly are we dealing with? We have, in most cases, we have proton exchange membrane fuel cells. It's one kind of fuel cell. It's basically mostly about how you design the membrane part in the middle. And for most applications in like automotive industry, for example, and aerial industry, it's PEM fuel cells. And the reason why is, of course, because we want to increase energy density. The only question is, how do we do it? And the most common solution is to use hybrid systems. So we have a fuel cell as a main power supply and batteries as a secondary power supply to serve power peaks, for example. But once we have a hybrid system, we also need to, control the hybrid systems, and that gives rise to the topic of energy management. And that is what this presentation will be about. And the reason why we need to have energy management is because by operating the hybrid system at the optimal efficiency point, we can increase endurance and optimize for endurance. By using the hybrid system in a smart way, we can ensure that we have sufficient power at any time. And also by using the two power sources in a healthy way, we can make sure they are not just falling apart after a couple of hours. And energy management strategies, they typically look something like this. We can start here on the left. We have the power profile. Either it can be recorded when you do simulations or in real time, in real life. Of course, it's just the instantaneous power demand. This goes as a set point into the energy management strategy. It has to be fulfilled that the power supplied by both power sources meets the power demand. And the energy management strategy determines either one set point for the fuel cell or two set points, one each for the battery system and for the fuel cell system. But of course, once you have one set point, you of course also know the other set point. And information from the battery and the fuel cell system is fed back as like data logging into the energy management strategy and can be used to determine new set points for the next instance of time. And there are different kinds of energy management strategies. And this is not the complete picture. There is, you could say, an infinite amount of branches. You could go into model predictive control. You could go into more machine learning. I mean, it's just ... So there's a lot to fill in. What we have focused on in our study is local optimization-based methods, as well as rather simple deterministic and fuzzy logic-based methods. So it's basically state machine and fuzzy logic. And that led us to a small project that we did on assessing the performance of energy management strategies. It was a collaboration between different projects in SMaRC. It was SMaRC from hydrobatics, it was RDL from electrochemistry, and me. And what we did is we gathered power consumption data with the Hugin AUV that is also one of the SMaRC resources. Then we used that power data to set up a simulated model of the whole hybrid power system. So battery, power converters, fuel cell system, and EMS, and of course the power consumption data. And then we implemented the energy management strategies and evaluated the performance. So here briefly about the test that we did. So this is the Hugin 3000 AV, and we've done tests outside Born on the Swedish west coast. We did what we would call a let's say maneuver test. So we performed a lot of different maneuvers at different speeds, turning rates, and so on. Went down here to deep water, did a few circles, a few zigzags. Then we performed dives and also steep dives, lawnmower patterns, simple squares, and collected the data. From that, we got a power profile, which we have segmented for our study. So you can see in the beginning, we have just started up the AV, it's in idle, and then we start the mission by going diving. So that's where we have the first increase in power demand. And then we have a transit phase. We do some different speed tests. So we go in a straight line, accelerate, and then go slower again, turning circles, zigzag maneuvers, a lawnmower at one speed. Here later, we have another lawnmower at different speeds, and different diving sequences. So going down and coming back up. And we use this as one power profile to evaluate the energy management strategies, but we also used it to extract segments from it and generate new power profiles that we could use, because the underlying power dynamics, they basically represent exactly what the Hugin AUV would experience in real life. So we decided to take a few of these lawnmowers and of those and appended them in certain ways, rather randomized. and used it to also evaluate the EMS. And that's the profile that we generated. So it's about 20 hours long, has a nice varying power profile. So the energy management strategy actually has to operate and work at some point. Yes, so that's the input to the whole simulation model, the power demand. And this is the simulation model. So we have, it's actually built from the SimScape toolbox, and it mostly consists of standard blocks. So the battery block for lithium-ion batteries is already fully implemented and validated. Same for the fuel cell block. And then the only thing that had to be added is power converters. We also modeled the parasitic power for the fuel cell balance of plant. We modeled the power profile, and we have the energy management strategies in the background. And then we have the energy management strategies. We have, as I said, the two simple ones, state machine or deterministic, and the fuzzy logic. And we try to use as simple and few regions as possible. So we have to find the region where we use the minimum fuel cell power, the maximum efficiency point fuel cell power, which is the nominal fuel cell power in our case, and the maximum fuel cell power that is able to be output. And we also use the same set points to design the optimization-based methods. So this is one of the methods that we looked at. It's a simple linear optimization problem. We have a weight times one power plus a weight times the other power. And the weights are calculated through these equations. So one is depending on where the fuel cell is currently operated, and the other one is depending on what the state of charge of the battery is. So if we have a low state of charge, like we can see here on the red curve, if we have a low state of charge, then we of course need to penalize the use of the battery system. So we make the system use the fuel cell at a higher rate, and yeah, with the effect that we can charge the battery. And in a similar fashion, we have also developed a second optimization-based EMS, which is using a quadratic cost function. It's designed on the operating point of the fuel cell in terms of a distance from the maximum efficiency point, and also some information about where the state of charge is and where it's headed and where we would like it to be. And using these four energy management strategies, we have evaluated on the power profiles that I presented. So here are some results. As you would expect, the two rule-based strategies, deterministic and fuzzy logic, they are very similar because nothing is triggering a change until at some point the state of charge drops low, and then of course the fuel cell operates at a higher level, and the fuzzy logic makes it operate a little bit smoother. But the two optimization-based methods, which are derived from the same set of rules and boundary conditions, they are much more sensitive. So they start being triggered either like after 2 hours, like this one, or almost from the beginning, and act very, very dynamic. And it has one interesting effect for use on long-range AUVs, because the state of charge changes accordingly. So we have the battery state of charge for the two deterministic methods. It's the red one and the blue one. And you can see in the beginning, it's able to maintain a rather high state of charge, but at some point, it just, let's say, loses it, and it drops to like 30% and finishes around 40%. And the two optimization-based methods, they have more power of enforcing fuel cell use. So we have the purple and the yellow curve, and you can see they are somewhat similar, but more like parallel. And they end up with a much better final state of charge as the two rule-based methods. And we can see, I think, similar behavior for the more complex mission. Showed you. It's not more complex. It is this one. So for this mission, we expect something similar to happen because we have a nice variation in the power demand. And there we are. So it's almost the same thing here in this case, because the overall power demand is a little bit higher in the beginning. Both rule-based methods are triggered a little bit earlier, around the 4-hour mark. And one interesting thing you can see here is because the state machine only has 3 or 4 regions. So once it's moving along a decision boundary, it's just it's like bang controller, just moving from low set point to high set point to low set point to high set point to low set point. And the reason why it's not going all the way up is because we have limited the rate of change of the fuel cell power. So it can't just go from, let's say, 500 watt to 1.2 kilowatt. In no time, it has a certain gradient, which is one of the ways to limit fuel cell degradation. And so before it actually reaches the high set point, it already returns to a lower set point. And the two optimization-based methods, they behave, again, somewhat similar, but are being triggered at different points. And if we look at the evolution of battery state of charge, we can see something similar again. The two optimization-based methods, they are better at maintaining the state of charge. But the state of charge is only one of the parameters that we looked at, because for the missions we analyzed, we looked at the energy consumption, the hydrogen consumption, the state of charge at the final, and the state of charge at the minimum, and the sum of absolute fuel cell transients. So we can see how dynamic is the fuel cell being operated, and also how the battery charging and discharging is by looking at the C rate. And I think the most interesting is that you can see the two optimization-based methods, they always consume more energy and more hydrogen, of course, than the two rule-based methods. But also they are better at maintaining the state of charge. So here we have minimum points of 50% and 37, and here 45 and 34. And we use the minimum state of charge as an indicator for how reliable the system is, because if you go towards, let's say, 10-20% on the lithium ion battery, you're pretty close to not being able to supply enough power to your vehicle. And of course, if you can't supply enough power, you're not fulfilling your mission. So it's one of the, I think, one of the key parameters to look at. And that left us with a few conclusions. I haven't written them down, but what we concluded is that the choice of EMS, so if we group them into optimization and into rule-based, then the choice of EMS should depend on the autonomy grade of the mission. So if it's a very sophisticated mission with a lot of challenging maneuvers and maybe even a lot of unknown maneuvers, so maybe you haven't really planned a mission before, but the vehicle is really intelligent and has to make decisions on its own, then we would propose to use optimization-based methods, because they are more expensive, but they are also enabling you to actually always operate at your full power output. While if you have a simple mission like a lawnmower pattern where you know roughly how much power and energy you need, you could probably use the simple methods, rule-based, and save a little bit of energy. And that concludes our work on energy management strategies. I have one more slide on ongoing and future work. Right now, I'm about to finish a small paper on fuel cells in practice and challenges and benefits for AUVs. Since we've done a little initial study on implementing a fuel cell on Lolo, we also have, let's say, quite advanced design on how to implement it, and we know what energy density we can get on the fuel cell battery hybrid system. And I think it's quite promising. So I'm about to finish that paper, maybe in 2 weeks or something. It has to be finished before New Year's. So time is running. And then in the future, next year, I would like to look into maybe some glider dynamics again, because it is interesting. And if it happens, maybe work on the fuel cell integration on our big demonstrator. Yes, that's it. Thank you.